Just focusing on various concepts of slope. What does it mean for slope? Um, and how does that transfer to calculus and our calculus notations? And of course, the various problems that we're going to cover this week. So in your traditional math, you studied y equals mx plus b. Now, what this technically meant here was that y was a function of x. Now, once again, why, why were the letters x and y chosen is not something that was like, oh, because it has to be x, it has to be y. That is not true. It's just y, and y is a function of x. As we have learned with a line, when talking about lines, when we have y equals mx plus b, what's important about a line is that this slope m, well, first off, it's a derivative of it, and this is m. It is a constant m everywhere for all x values. In other words, it doesn't matter where I look on a graph, right? It doesn't matter where I look on my graph, the slope is m, or actually f prime is m, f prime is m, f prime is m. The definition of technically of a line is a function where the slope is a constant. Now we call that m. And so when we were looking at the derivative, we were looking at f prime of x, which is m. Now, what has gotten a lot of people confused as well and don't have a full grasp yet is that when I'm saying this f prime of x, because it's inferred in all of these problems that we are talking about dy dx. Now, you've studied now in an equation. Now, when you did it with the slope over here, you did it with like delta. When you did using slope triangles, you did delta x, delta y, and therefore the slope was equal to delta y over delta x. This is where we get to the dy dx. Delta xy over delta x is always the same in a line. So when we were doing just lines, you were technically always finding dy dx. Now, dy dx is really at a point, all right? So at a specific point where this one is over an interval. However, because it's a line, the average rate of change equals the instantaneous rate of change everywhere. That's only true for a line. This is the average. This is the instantaneous. Okay. So you've studied slope. How do you find a slope? Rise over run, delta y over delta x. In reality, because it's a line, what you've been finding in all of those problems was the derivative dy dx. Now, I've shown you this notation. Dy dx is really d dx of y. But more importantly, this means the derivative of y with respect to x. Okay, and I've said that over and over and over. But what does that mean? Well, this more specifically means the change in y, and this is also the definition of the slope m, okay? The change in y when x increases by 1 unit. And this is what dy dx refers to. How does y change at that point when x increases by 1 unit? This is a very important definition of slope that you should have. Now, sometimes you can say it in reverse order. You can say that when x increases by 1 unit, y, so forth. Those of you who were with me in AP Stats, you also had this type of work in regards to regression lines, but of course that was a model. This is exact, but it's the change. What is slope? What is the slope? What is dy dx? It is the change in y when x increases by 1 unit. Now, most of you define the slope as this, because whenever we were talking about slope, we were always talking about y as a function of x. Okay? Now this has a lot of important features here, right? So if dy dx is greater than 0, what does that mean? And this is actually a topic we're going to cover in a future unit. What does that mean if dy dx is greater than 0? What does that mean? Now I'm asking for some feedback.
Is the slope increasing?
You got to be careful. The function is increasing. We'll talk about what because the slope is positive, but the slope is not increasing. That's something different. So we'll be careful on that. That's in our next unit. But the function is increasing, and more importantly, that if I were to draw a graph, it would look like this. Because if x increased by 1 unit, I know that the delta y is something positive. If the x goes up by 1 unit, meaning that, and when we see x increases by 1 unit, basically that just means that we read left to right when we talk about slope. So we always go from the left to the right, and so when we read the graph, if it goes up from the left to the right is what we are referring to, because we're always investigating what happens when you move over to the right by 1 unit. So there's those type of parts. If dy dx is less than 0, what does this mean?
If the function is decreasing, the slope is negative.
Because once again, we read from left to right, and so when we go over by 1 unit on the x, the y has some type of negative slope. The y value goes down by a number. It's negative. When we're always talking about x increasing by 1 unit. Now for the ones that become a little bit more troubling, what some of you saw in your homework, but some of you were having some issues with because you hadn't seen it or practiced it. If dy dx equals 0, what does that mean?
Is it like a horizontal line?
Yes. It's a horizontal line. Perfect. And a horizontal line looks like this. The slope is 0 because when you go over by 1 unit, delta y is 0 in this case. Now, what's important and interesting in this case is, let's say I was trying to find the equation at this point right here, x at this coordinate, at this coordinate h comma k, where x equals h when y equals k, then the equation of this line, when the slope is 0, is y equals k. Because no matter where you are on this line, no matter where, y is always going to be equal to k, y is equal to k, y is equal to k at every single point. You saw some of these problems and this has popped up a couple of times, that when I asked you for the tangent line and you got a slope of 0, then the answer always turns out to be y equals whatever the y value was, or it was f of a. So we had said like y equals f of a when we're talking about tangent lines. The next one is what gets a lot of people misunderstood here, and this is going to be very helpful for us. Dy dx is undefined. What does that mean?
It doesn't exist.
What does that mean? It means doesn't exist is a different thing. Doesn't exist is with derivatives, or what is with limits. What is dy dx equals undefined? Well, this is also the same thing as dx dy is equal to 0. X does not change when y increases by 1 unit. So now this is the opposite, because over here in this previous one, y does not change when x increases by 1 unit. So what does this look like?
Vertical line.
It's a vertical line, yeah. And as we'll learn as we go into on Wednesday, a vertical tangent. So this is what happens when dy dx is undefined. Because what you're saying here, once again, what you're really saying is that dx dy is equal to 0. Because when we talk about the delta y over delta x, well, the delta x is 0 because it's never changing. So you get some constant over 0. which is the reason why you get that undefined. So when you get an undefined slope, or you know, sometimes you might interpret that or say it, even though it's not technically right, but it's okay to, it's not a killer, does not exist, then what you're dealing with is a vertical line. It doesn't technically have slope because you can't walk on it. All right, we define something that's differentiable as a slope that exists, which means that you could stand on it. Basically, that's my definition on it. If this was an actual something that you can be on, you can actually stand on it. So you couldn't stand on a dy dx that is undefined. And the equation for a vertical line is x equals h. So horizontals are y equals, because the y value is the same everywhere. Verticals are x equals because x is the same everywhere. Okay, so horizontal. Now we're still got more to go over, but I think hopefully, you know, at least when it comes to horizontal lines and the idea of this dy dx, when we're talking about it in a more traditional concept, how much y increases when x increases by 1. When we say dy dx, that is what we are saying. Y increases by blank when x increases by 1, and that answer to that blank is whatever the slope is. So if the slope is 5, we're saying that y is increasing by 5 units when x increases by 1 unit. So that's the real meaning of the dy dx. And if we switch the letters now, it all means the same. So when we had a problem where it said, all right, dA dB, and the question is, okay, what is dA dB? Well, this is asking me, what does what? What does A change by when B increases by 1 unit? Because you don't always have to be dealing with A and B, or X and Y. Sometimes you might have a visual, as we will see. It's called related rates, but we can even talk about rates of change. It's our next unit. Or actually, is that our next? No, it's 2 units from now. So, for example, you might be dealing with a picture that looks like this, and this is A, and this is B, and you see how it doesn't follow the X and Y coordinates. So here's X, the X-axis. Here's the Y-axis, but our images look, it's angled to the side. So when we say dAdB, we're asking, you know, what is A changing? So if B increases by 1 unit, how much does B increase by? Is the question that I'm looking for. So if B is increasing by changes by 1 unit, how much does A go by? And this idea of rotational or transformation, that we're not always on the X and Y plane, we're not always going left to right, top to bottom, up and down, left and right, we can have these same questions for here. The same thing goes that if I said, hey, dH dt equals 7, then this says that H increases by 7 when t or every 1 unit of time. So, I mean, you could say, I could have said the exact same words, but it was like every second, for example. Say, let's say if t was in time, then I would say h is increasing by 7, whatever the units are for h, um, every second. Put those quotation marks right here. There, it looks better. H increases by 7 units, 7 feet, for example. So if h was in feet and t was in seconds, and we're going to get into this applicational work later on, then we would say that h increases by 7 feet every second. So when we're talking about, everything doesn't have to be x in a function of y. And so that's when we were talking about these variables about dA, dB, or, d, dr, d theta. It's how you're measuring the changes. So, most of the time is going to actually be our real, in practice, time is our independent variable. Time moves forward, and as time goes forward, we're wondering how certain things are changing. So this is a topic technically that's called rate of change. When we study all of the ideas when they're changing with respect to time, we'll get to that, and then we talk about how these different rates or these different variables can therefore change in relationship to each other as well as time. Okay, so I hope that does a somewhat decent job of explaining why the letters aren't always X and Y. Everything doesn't have to be going left to right, up to down, but that's what slope refers to. We're referring to that the bottom variable is increasing by 1 unit. So if that bottom, whatever is on the bottom, if it's X, if it's Y, if it's T, if it's B, we're saying that bottom variable is increasing by 1 unit. So how much does my dependent variable change by when that occurs? And that's the concept of slope. Now, if we're just talking about equations of lines, then dy dx is our basis of doing things. Dy dx is positive slope. Dy dx is negative slope. Dy dx is 0, horizontal line. Dy dx is undefined, vertical line. Parallel lines. Now, in our definition, just to remember, the note, we also use this symbol right here, an upside down. Oh, oops, that's the wrong line. We use these two little lines next to each other for parallel lines. So, two lines that are parallel have what?
Same slope.
So if I had y equals f of x and y equals g of x, then f of x is parallel to g of x when f prime of x is equal to g prime of x. And remember that if f or g are lines, then their derivative is equal to m. is equal to the slope of that line. So if it's a line, then it's the slope of the line. You'll see that in one of the problems. I'm going to say, here's a function that's not a line. When is this parallel to this other line? But I can also give you just two equations. I can say, here's a function, here's another function. When are the, oh, I did the wrong symbol again. Sorry. So f of x is parallel to those when we have it. Now, what these problems are going to traditionally look like is that the second function g in when we get to next week, this will be some y equals mx plus b, and so therefore you're going to try to figure out when is f prime of x equal m. So that's technically how the problem will look like. One of them will be some type of function, some non-linear function, and then the other one will be some equation of a line written in, it doesn't always have to be written as y equals mx plus b though. It might be written like ax plus by equals c, standard form, or a point slope form, and you have to figure out in terms of what the slope is, and so parallel lines, that's the main part that you're going to be working with. Perpendicular lines. What about perpendicular lines? Two lines are perpendicular if what?
The slopes are opposite or reciprocal?
If their slopes are opposite reciprocals. Opposite meaning opposite sign. Reciprocal meaning that the flipping of what was in the numerator becomes into the denominator. So f of x, oh sorry, and this symbol right here is the upside down t. F of x is perpendicular to g of x when f prime of x is equal to negative 1 over g prime of x. Now, as I stated before,
Mr. G, you put the wrong symbol.
no, that's the correct symbol. I fixed the ones from the top. Parallel is two lines, and perpendicular is the t. And I said, oops, let me fix those ones up here. So let me pause right there in case anybody has to correct those ones. Okay. So y, I'm going to give you like y equals f of x, and I'm going to give you like y equals g of x. But in your homework, traditionally this right here is a line, which means that g prime of x equals m. And so when solving these problems, you're going to set f prime of x equal to negative 1 over m. That's basically what we're going to do. You're going to, oh, here's the slope of this one, because technically you're finding the derivative of both functions. But if it's a line, just solve for y equals to determine what the slope is going to be. Oh, the slope's going to be 8. So I'm going to set the derivative to negative 1 over 8. Oh, the slope is negative 2. So I'm going to set the slope to positive 1/2. Now the negative does not mean that it's going to have a negative number, because if the slope is negative, it changes the sign to the opposite. All right. So if the slope was already negative, then the perpendicular slope will be positive. And this comes from a visualization that if here's one line, my perpendicular line looks like this. And of course, yes, they do intersect at a 90-degree angle. But if we have these two lines, line 1 and line 2, then the slopes of line 1 is equal to negative 1 over the slope of L2. Now, I could have also said that the slope of L2, of line 2 is equal to -1 over the slope of line 1. I could have it goes hand in hand. You don't have to say that. You always speak one to the other. The math works out so that if you were to solve for the other slope, you would get the same thing of -1 over as well. So this week, I'm going to be asking you things about horizontal tangents. I'm going to be asking you things about, which means that the slope is 0. I'm asking you about vertical tangents, which means the slope is undefined, or hence dx dy is equal to 0. And I'm going to put in problems about talking about some relationships between two functions where we're wondering when they're parallel or when they are perpendicular. Hopefully, as well as you have a good solid understanding now that slope refers to when that independent variable increases by 1 unit. We're asking about what is the dependent variable changing by, and hence it does not always need to be x, y as a function of x. We're going to get back into implicit differentiation tomorrow. Tomorrow will basically be the same implicit differentiation lessons that you have already learned. All I'm going to do in tomorrow's lesson is we're not going to deal with polynomials. We're all going to be dealing with the transcendental function. So all your derivatives tomorrow's homework, which is a handout, will be sines or cosines, tangents, or exponentials, or logarithmics. So those were the functions that you'll see in tomorrow, and every one of the problems tomorrow, it'll be those. We'll go over some examples of how it works. It works the same if you've been doing all the work with implicit differentiation with the problems you've done now. You're just applying those other differentiation rules to these new functions. And then, of course, we'll continue on as the week goes on. That's all I have for you for today. Have a great rest of your day.